All right, welcome back. This is part 5, right, of our lectures. Or actually, it's part 7, I believe. We recorded already 6 of them, so this is part 7. So in the previous part, we looked at how you put a picture on the categorical data. Categorical meaning it's either ordinal or nominal, right? So one of the most popular techniques is the bar chart. So here's an example of the bar chart. And today, in this part, we're going to talk about how do you put a picture on the interval data. One of the most popular techniques for the interval data, how do you represent it on the chart, on the graph, is also a bar chart, but it's called histogram for numerical or continuous data. Okay, and let me actually show that in form of slides like that. All right, and the problem is, of course, continuous data does not naturally fall into any categories, right? So in the previous example, when we looked at distribution of business school graduates, where they found the job or employment in accounting, finance, etc., right? Naturally, all of our observations were falling into one of the categories. It's either accounting or management or marketing or other, okay? When you have numerical data, you don't have categories. These are actual numbers. So therefore, there are no natural categories, right? So therefore, for numerical data, we have to artificially create categories, right? And basically, the way it's done is we have to find out minimum number in our data set and the maximum number in our data set. So basically, the entire range, right? And after that, we have to decide into how many intervals we want to split the range. So for example, let's say I have a range of numbers from 0 to 100, like scores in the class, right? Cannot be less than 0, cannot go higher than 100. And I want to see the distribution of grades, of scores in the class. What I can do is I can define the, like let's say I want to go by letter grade, A, B, C, D, E, etc. So typically what happens is A is from 90 to 100, right? It can be A minus, A plus, that kind of deal, but it's an A range, right? From 90 to 100. B range is from 80 to 90, right? C range is from 70 to 80. D is from 60 to 70, etc. So what I can do is define my ranges, and basically after that all I have to do is count how many scores fall into every category. Let's say I have 30 students in class, and out of these 30 students, 4 got A's. So they scored between 90 and 100. So therefore, in my group, in my bin between 90 and 100, I'll have 4. Right? The count will be 4, and I have, let's say, 17 B's. So therefore, count from 80 to 90 is going to be 17. So, in other words, for numerical data, for continuous data type, I pretty much define categories myself artificially. And then after that, I treat my numerical data as categorical. Okay, so in a sense, it's actually dumbing the data down somewhat. Why? Because I'm just counting how many B students I have in class, right? So therefore, I'm counting out of 30 grades that I gave out, how many students scored between 80 to 90. In a sense, I don't care how close they are to the borders or to the middle, right? If somebody scored 81, somebody else scored 88, they're still between 80 and 90. So therefore, within this interval, I lose visibility, right? I don't care really. Maybe they're all bunched up against the lower limit. They're all close to 80. Maybe they're all close to 90. Maybe they're all close to the center. I don't care. They're all between 80 and 90. That's the only thing that matters for me, right? So when I'm kind of creating the histogram for numerical data, I'm a little bit losing information. Okay, I don't really care where numerically they're located as long as they fall into the same, into certain interval. Okay, so creating the histogram is dumbing a little bit the data down so that we can create bins or categories, and then after that we're going to plot the bar chart just the same as we did for nominal and ordinal data. Okay, so let me illustrate that. There is a data set called phone bills on the blackboard, and it still says SAV, which basically means SPSS. And we didn't use SPSS, so it's actually Excel. All right, so go ahead and download the data set from Blackboard. It should be phonebills.xls, okay? I have it actually right here, so I'm going to open it up from my computer. And there is my Excel data set. So let me make it bigger. Oh, it's not showing, right? Okay, hold on, give me a sec. That's what I was afraid of, it's not showing. Okay, and we're back. All right, so this is my data set, right? It has a number of phone bills. So all of these are numbers, right? In dollars and cents. So the first customer who we had in our data set paid, and it's monthly, right? Monthly service. $42.19 for 19 cents for their first month, okay? And next one is $38.45. So these are not huge or not small bills, so these are reasonable, right? At the same time, note that we have sometimes some weird observations, right? Such as $118.04. That's a little bit high for the phone bill, right? So we don't know what's the deal here. Maybe they were making some long distance or international phone calls, right? Or maybe they have a bundled service, right? It's not just a phone bill, maybe internet as well, and the basic cable. At the same time, there is another weird observation, zero. How is that possible? Is it possible to pay $0 on your phone bill?
Yeah, he's using the neighbor's line.
Yeah, if you're using the neighbor's line, that's possible. Or it could be the first month, right? Somebody just signed up and the phone company says first month is free, right? So they didn't pay anything, and then from second month, basically it starts. Or maybe, when we were conducting the experiment or collecting this data, people who collected the data, they called people to ask them about, how much money you're paying on your monthly phone bill. Nobody answered, but they said, well, you know what? I still want that to count, so how about I enter 0? Doesn't matter, right? Who's going to care? So it can be a data collection issue. It can be actually the real $0 service phone bill, right? Because it's the first month. So we don't know, right? But that looks weird a little bit. So therefore, every time when you have data, it's kind of a good question to look at the data and see if you have any unusual observations. And they're called outliers, right? Today we're going to actually take a look at how do you formally define an outlier. So outlier is unusually large or unusually small number. Okay, that's great, but is 0 an outlier in my case? Is it unusually small? Is it much different from the rest of them? I don't know. Or on the other hand, is that an outlier? 118. That seems too much to me, but is that technically an outlier? I don't know. So we're going to find a way to formally define what is an outlier. Okay, but let's plot the data, right? That's what we were planning to do. So I'm going to go back to jump, and just like we did in the previous case, in the previous example, let's import the data from Excel file. So click on the open icon, and then just browse to the data set. So I'm going to see where I can find my phone bills right there. Whoops, apparently I clicked the wrong thing. Okay, phone bills. And it says this is how it's going to look like. I'm fine with that, so I'm just going to say import, and here is my data set. Okay, the modeling type for the data set by default is continuous, right? Because these are numbers, right? So if these were words such as poor, fair, excellent, etc., then probably it would be different, right? Probably it would be nominal by default. But since these are numbers, Jump says, okay, I'm going to just say that these are all numerical data. And if the user wants to change that later on, they certainly can do that. So by default, it offers me the continuous data type, which is what it's supposed to do. to be, right? So now I'm going to plot the distribution of these variable bills. All right, so I just click on that button or go to Analyze Distribution. It does the same thing, right? So here's the shortcut. And the only thing that I can see is column called Bills. And I just click right there where it says Y columns, moving it into the working area, right? And then I click OK. And here is the histogram for me, ladies and gentlemen. Okay. Now again, it's vertical, right? Because that's what default view is. So I mentioned that before. I believe we can go to the settings and change that so that every time when it plots some distribution for us, it's actually horizontal. And how do we turn it? Go to the distribution, red triangle, and say stack. Okay, so this is my histogram. So let's see what JUMP did with my data. I had 200 observations, right? That's my N. N is the sample size. So this sample has 200 observations. Okay, these 200 observations, I can pretty much see how they were broken up, right? So by default, what JUMP did is, the first number I see here is 20, right? And 20, before 20, I have two different bins, right? Two different categories, okay? So the default size, therefore, for this chart specifically, is 10, right? So JUMP basically said that all of my numbers, and we can see them right here, okay, in the quantiles, all of my numbers were somewhere between 0, which is the minimum, and $119.63, which is the maximum. So somebody paid almost $120, right, on their monthly phone bill. That's a lot of money. Okay, so JUMP after that said, okay, our range of all observations is approximately $120, right? So let's split that in 12 equal ranges. So the width of the range is going to be $10. That's why from the first range is from 0 to 10. So all bills that are less than $10, right, they will be falling right here, okay? And we can see that, or we can't see that yet. This is the highest count, right? Let's actually show the counts. How do we do that? Same as in the previous example, right? We go to the bills, say histogram options, show counts. And it will show me how many numbers fall into every one of these bins or categories, right? So out of 200 numbers, I had 52 bills which were between 0 and $10, right? And this is how we lose visibility, the point that I tried to emphasize previously, right? I don't know really what are the numbers, right? Well, I do actually. If I go back to the data set, they're all there. Okay, how can I find them? I just click on this column, right? And after that, I can go back. All of these bills are highlighted for me, right, in my data table. So I can actually find them in my data set. But looking at this chart, at the histogram, I don't really know where these bills are. Maybe all of them are zeros, right? Maybe only a handful of them are zeros, and then some 5s, and then I have 9 and 10, right? Could be. So I don't know by looking at this chart where the numbers in this tight range between 0 and 10. That's what I meant by we're losing visibility a little bit when we're dealing with histograms, right? So it's kind of taking the interval data and saying, let's make ordinal data out of that, right? Actually, we're going to kind of, every bill is classified as the one between 0 and 10, or 10 and 20, or 20 and 30, etc., right? So we're kind of have a bunch of buckets where we place every bill, and each bucket is $10 wide, right? So let's kind of briefly discuss how does software choose how many bins to have. In this case, we had 12 bins, right? 120 is the range. The bin is $10 wide, so 12 bins, right? What will happen if I have very few bins? For example, I could actually split this whole range into just 2 bins, right? From 0 to 60 and from 60 to 120, right? Is that a good thing or is it a bad thing? Not good, right? Why?
You don't have enough granularity to see this.
Exactly, you don't have enough visibility, right? It's basically, it's too crude of the tool, right? It says why, literally it's going to be step 1 and step 2, right? So it's going to be pretty ugly histogram. And therefore you will not be able to tell much about what is going on, right? So having too few of the bars is not good, right? What about having too many of the bars? So for example, what if I will go, instead of width of the bean $10, I will go 50 cents, 0.5 of a dollar. What do you think will happen? You will have a lot of noise going on, right? You will have a bunch of bars, and some of them will be very low because you don't have anything in these ranges, right? And some of them will be pretty high because you have a lot of numbers. So they will be jumping up and down all over the place, okay? So all this random noise that you will see in the data that you have collected, you will see reflected in your histogram, right? So therefore, it will show you probably how the things are distributed, but it will also pick up some random things that are specific to your selected sample. So too few bars is not a good thing because you don't have enough visibility, and too many bars is not a good thing because you're starting to pick up noise and it looks ugly, okay? So therefore, there is actually a formula called Sturlitz formula, I believe, that, yes, Sturgis formula, right? Sturgis formula that defines how many, what's the optimal or best number of beans to have. And it has to do actually with the number of observations. So it involves natural log of number of observations that you have. So in our case, it was 200, and the software says, okay, using the Sturgis formula, 12 beans is the optimal thing to have. But we can actually modify the number of, not the number of beans, but the bean width and the number of beans, obviously, right? So let's see how we can do that. Let's say, for example, that I want my number of, my width of bean instead of $10 to be 15, okay? How can I do that? Well, if you go to the red triangle, the second one, bills, and I believe it's in the histogram options, okay? One of the options says set bean width. And if I click on that, it brings up the dialog. Right now it says 20. I don't know why, quite honestly. But let's change that. So right now I have 10, right, as the bean width. So let's go ahead and change that to 15. Okay? So right now I have 10, right? And I have 12 beans. When I change it to 15, what will happen? Well, I have less beans or more beans? Bars. Less, right? So the histogram is going to be less detailed, somewhat less detailed, right? So when I click OK, and indeed some of the bars disappear, and part of my old bar is actually highlighted. So if I click outside somewhere, it unhighlights everything, okay? So it's less detailed. I lost a little bit of visibility, right? But it still shows me kind of nice picture, right? And what do we see from this picture? I mean, this is how your data is distributed. This is the picture of your data, right? In some aggregated form. How?
Sorry.
Yeah, go ahead.
Is the upper 95 mean, is that the confidence interval?
Yeah.
Lower, upper?
Yeah. One. Oh no. These ones?
No.
Oh, right over here. Yeah, that's the confidence interval. Yep. So that's how we're going to find out the confidence interval. Couple of days down the road. So by default, it does give you the confidence interval. So how can we use this data? Well, first of all, let's actually change the view. Instead of counts right here, I'm going to show percentiles. Okay. So I go to the histogram options. I unclick show counts, and after that, I'm going to show percentiles. Okay. So what do we see? Let's say I'm an executive, right, at the phone company, and I want my employees to give me the distribution of the phone bills. Now, phone market is saturated, right, pretty much. I mean, I have the landline, for example. Am I going to get the second landline? No, not likely, right? So therefore, you can't sell more, phone services to the customers that already have phone services, right? That actually is true about the landline services and about cell phone services, right? So right now, the battle between these gigantic companies, such as Verizon, T-Mobile, AT&T, they can't acquire new customers, not in the US, right? It's just basically redistribution of the market. So some people who are on the contract right now, contract expires, they will either stay or they will switch to the competitor, right? So right now, the battle between these companies, at least in the cell phone service area of their business, is market redistribution. That's what it is, right? They, of course, can offer more services by themselves, right? They can provide you high-speed internet. They can provide you, television subscription for different channels, whatever, cloud services. Can provide more and more products, but as far as the cell service is concerned, it's just basically stealing customers from each other. That's it, right? So let's say I'm an executive of one of these companies, and I ask my employees to find out how much money people are paying for their services. Obviously, we can't get the entire population, right? We discussed that in the previous several classes, right? Because that would be close to impossible task. 320 million people, you will not ask everybody, obviously, right? So here's your sample, 200 observations. What can we see from this sample? Well, we can see that on my low end, right here, okay, 36% of people are paying under $15, right, on their phone bills. 19% of people are paying between 15 and 30. So if I add these two together, what am I going to get? 55%, right? 55%. So a little bit over half of the customers are paying $30 or less. And if I want, for example, to persuade them to switch to my company, how can I do that? Phone service is a phone service, right? You pick up the phone, you dial a number, you talk to the person on the other end. There's not much difference between companies, right? So the only thing that I can compete on is price. If people are already paying $30 or less on their phone bill, do you think I can offer them an attractive deal to persuade them to switch over to me? Like, I can save you $5 a month, can you switch to me? Probably they're not going to go for it, right? It's just not worth it. So this, and this is more than half of the customers, right? So that's probably not a good target for us, right? It's very hard to persuade these people to switch because you offer them lower monthly payments, right? And then we can see that in the middle, we have only a few, the percentages are relatively low, right? So middle range of bills, not a lot of people are paying that, okay? And if we look at the high end of the distribution, what do we see? Here we have 7%, here we have 14, that's 21, right? And here we have 9, 30% actually, okay? So almost 1/3 of the customers are paying $75 or higher. So that's actually a pretty good chunk of customer population, right? 30%. And $75 is a lot of peanuts, right? Strictly speaking. Well, $100 is a lot, right? 120 is a lot. So therefore, here is probably my target group, right? As an executive. Well, I can target these customers, but it's just not a lot of them in the middle range, right? So there are only 17% between 30 and 75. But there are a lot of people who pay unusually high amount on their monthly phone service, right? So that's probably my target group, right? So the bottom line that I want to emphasize here is that looking at the distribution can tell you something about the subject matter, right? It can give you insights into what's going on in the market. So it's not just an exercise and let me put up a nice, cool picture and look at the data and see how it's distributed. It can actually provide you with valuable insights, okay? So any questions about the histograms? How to plot them and how to change their width, how they look, how to show up numbers or percentages?
What is the red mark?
Red mark right there? Yeah, that's a little bit weird. That's, according to JUMP, this is a 50% of the most dense data. Yeah. So that basically tells you that the majority of observations are right here, okay? Gives you the boundaries. And by the way, this diamond also, kind of what is it, right? Diamond is actually, the middle of the diamond is your mean, and these two things, the ends of the diamond, are the upper and lower boundary of the confidence interval. So this is a confidence interval right there. Yep. All right, so let's also talk about the shapes of histograms. So I'm going to skip through the slides because essentially they are they basically repeat what I just said. Okay, so this is the distribution that we just saw, and this portion of customers are hopeless, right? We will not target them. They will not switch because of saving $5 a month. But this is our target area. Huh, Phil?
So for just on PowerPoint manipulation, how did you just do a screenshot of that and put it in PowerPoint?
Yeah, what I did yesterday is this, actually, when I modified my PowerPoint. Remember we did this tool, so if you go here, click the selector, and after that I can select the whole thing and then copy that and paste back. Yep, that's what I did. All right, so let's talk about how do you characterize the shape of the histogram, okay, shape of the distribution. Okay, well, first of all, histograms can be symmetric and not symmetric, right? Well, not symmetric, we say asymmetric. So symmetric histograms can look like that, okay? This shape is actually going to be very popular later on when we're going to discuss distributions, right? What does it look like? You probably know this distribution from the Math 125 that you took. This shape right there. Bell curve, right? Or normal distribution, right? Well, it doesn't look much like normal, but in general, it kind of resembles normal distribution, right? How does this distribution look like? What's it called? Uniform. That's exactly right. It's flat. Basically says that any number between lower boundary and upper boundary is equally likely, right? And this is also a symmetric distribution. It's kind of a little bit unusual. Well, it looks a little bit like the bills, right, that we just considered, phone bills, right? So you have a big spike going on right here at the beginning of the distribution, big spike, and kind of a valley in the middle. Sometimes when I grade my exams, I see that type of distribution as well. A lot of guys with C grade, a lot of guys with A grade, but in the middle, B's, not a lot. But that doesn't happen very frequently, but occasionally, every once in a while, I have this unequal distribution of grades in class. That's weird. All right, so symmetry, right? Now, if distributions are not symmetric, then they are called oftentimes skewed. So these are good examples of skewed distribution. Skewed means that it has a long tail going either into the right area, positive area of the horizontal axis, or towards the left in the negative area. So therefore, if distribution looks like that, it's called positively skewed. So skew direction is where the tail is pointing. So if the tail goes to the right, it's called positively skewed because it's in positive or right direction. If the long tail happens right here, then you can...
I thought that was counterintuitive, but you would think it would be skewed to the left.
Yeah, because on the left you have a bunch of observations.
Statistically, that's not correct.
Yeah, that's right. But that's just a custom. Statisticians just said, okay, let's do it like this. Where, yeah, where the tail goes... Yeah, where the tail is, that's the direction of the skew. It's right or left. Okay, so let's kind of discuss what kind of distributions can look like that. Salaries in the society. Do you think how do you think salaries in the society are distributed? There are people who earn little money, right, working at like gas stations or waitresses or waiters at the restaurant, and there are people who are like doctors and lawyers and executives that earn a lot of money, right? So if you would have to pick between these two distributions, right skewed and left skewed, right skewed, right? Yeah. So salaries in the society probably are distributed like that, right? A lot of people earn not a whole lot of money, right? There are a lot of these people. And then as you get into the higher and higher and higher salaries, there is progressively less and less percentage of people making huge amounts of money, right? So therefore that can be actually, I believe at CNU, you can find salaries at CNU is a public data, right? So you can find them on the internet because CNU is a public university. And there is actually a histogram pretty much exactly like that, the distribution of salaries at CNU, okay? So let's kind of think about the example of what can be distributed like that. So
our salary is off the chart. Our salary is off the chart.
Yeah, probably. Yeah, adjuncts, their salaries are pretty much right here. Yeah, past that. Yes, they're outliers, right? Yeah. Oh, it's okay because secretaries people who work at the registrar's office, their salaries are not huge by any stretch of imagination. Yeah, so they probably represent these couple of bars right there. Okay, so negatively skewed. One example that I can think of is amount of money that you spend on the car maintenance. When the car is brand new versus mileage, right? Versus mileage. So if the car is brand new and it has low mileage, then you have very few breakdowns. Every once in a while you need to change oil, you replace the tires, right? If something goes bad, it's still on warranty, you drive, to the dealer, they replace it at low cost or no cost at all. So the cost of maintenance when the mileage is low is small, right? But as the car is getting older and older, a lot of things start to break down, and at some point in time, pretty much everything fails, right? That's when you have to sell it at the residual value, right? Whatever you can get for it, maybe from the mechanic, sell it for parts, right? So that can represent the amount of money that you spend fixing the car versus mileage, right? So this is distribution of salaries. As the salary gets higher, number of people get lower, right? And that's number of repairs versus mileage. As mileage gets higher, number of repairs or amount of money that you spend is getting more and more and more, right? So that actually is very practical. So oftentimes when you plot the histogram, when it looks skewed to the right or to the left, you can kind of think about the valid, well, let's call it business reason behind that, okay? Another part of the characteristic of the distribution is modality. Modality is how many peaks the distribution has. It actually has something to do with the mode. After the break, we're going to talk about the mode, median, and the mean. Mode is actually the most frequent encountered value in the data set, okay, or tallest bar in your histogram. That's called the model class. Okay, so these histograms that we looked at, this is unimodal because there is only one peak. Well, here we have no peaks, so technically it's probably unimodal, right, as well. This is a bimodal because there is peak 1 and peak 2. And that looks a lot like Beal's distribution, phone bills, right, that we discussed earlier. So that's also a bimodal distribution, okay? Modes do not necessarily have to be the same height. So one can be kind of small peak, another can be taller peak. That's still a bimodal distribution. And skewed distributions like that are unimodal because there is only one peak, right? Okay. And bell-shaped histograms, well, later on, tomorrow actually, we're going to discuss special distribution. There is a very special distribution in statistics. I always call it a celebrity in the statistical world. Okay, it's called normal distribution. Well, you know that from the Math 125, but tomorrow we will discuss, tomorrow and actually next day after that, we're going to discuss something that's called central limit theorem, and that's what makes the normal distribution so special, okay, the central limit theorem. The fact that if you increase your sample size, your sampling distribution is going to look more and more normal. So in the limit of large sample sizes, your sampling distribution starts to look normal no matter what the original population distribution is. Okay? So bell-shaped distribution therefore has a special meaning in statistics. Bell-shaped distribution, as you can see, symmetric, right? Number one. Number two, it's unimodal, there is only one peak. Okay? And it goes down to almost zero on the left side and on the right side. Okay? So 3 ways how to characterize kind of verbally, right? Your histogram is symmetry, if it's symmetric or not. If it's not symmetric, is it unimodal or bimodal? And also, what kind of skew do we have? Do we have right skew or left skew or no skew at all? That also is a possibility, okay? So let's stop this section right here, and after a short break, we'll start talking about numerical descriptive statistics, okay? All right. Welcome back. So, in this part, we're going to switch gears a little bit. So far, we discussed how to put a picture on a data set, right? And we didn't do a lot, actually. We discussed pretty much bar charts, right, as they apply to the categorical data, and we call it simply bar chart, or numerical continuous data, and then we call it a histogram, right? There are, of course, other methods, right, how to put a picture. For example, bar chart. bar chart, I believe, is viewed largely as one of the most useless and uninformative ways to represent the data. Especially in 3D, it may look very cool, but it's hard to read and it can be misleading, right? So statisticians are not using that a lot. So today, well, in this part of this class, we're going to talk about numerical descriptive statistics. So not just provide a picture for the data, but characterize it with several numbers, right? Okay. First of all, let me point out from the get-go that the majority of the things that we're going to discuss in this part, they apply to continuous data set. Because continuous data set is the most rich one, right? We discussed it in the previous couple of lectures that numerical or continuous data set is highly privileged because we can do all kinds of computations with it, right? We can compute averages, medians, standard deviations, coefficients of variability, what have you, okay? So therefore, the majority of measures that we are going to discuss today in this part is applicable only to interval data, okay? All right, so I believe actually I have another slide. No, probably not. Okay, first of all, so here's the plan. Where's my marker? We're going to discuss three things. Number one is central location. Central location, measures of central location. Number two, measures of variability. Variability. And number three, measures of relative standing. Relative standing. Okay? So let's start with central location. Central location simply tells you where is the center of your data. Okay? So your data set, we've seen that in the previous example, right, with cell phone bills. Data is scattered all over the place. Okay? It ranges from $0 to almost $120 per month. But what is the most typical observation? Okay? So where is the center of your data? The place towards which most of your data points tend to gravitate. So the most simple and most popular actually measure is called mean. Sometimes called arithmetic mean, sometimes called average. Very easy to compute. I'm sure you did that in Math 125. You just add all of your numbers together, right? And divide it by the number of observations. So in my previous example, I had 200 phone bills, right? If I add them all together, divide by 200, that would be my average monthly phone bill. That would be probably somewhere in the neighborhood of, I'm guessing, $30, maybe $40 or something like that. Okay? So very easy and very popular. Now let's discuss briefly difference. Remember, in the previous couple of classes, we discussed difference between population and sample. We said population is the holy grail of statisticians, right? If you have data for the population, that's it. That's all there is out there, and that's all you need, really. You can compute all kinds of things from your population data. So, for example, if you compute the average from the entire population, that would be a true population average, and we're using statisticians, and we are statisticians as well, right? We're going to use the letter mu, Greek letter mu, to denote the mean for the entire big fat population, which we never can get, by the way. In most of the cases, this is our goal that we cannot achieve. The average for the population is what we want to know, but unfortunately, we don't have the population data, so oops. All right. Also for the population, we're going to use capital letter N for the population size, right? So for example, let's say I have 160,000 people living in the city of Newport News, and I want to compute the average salary. If I get all the numbers, my N is going to be 160,000 people, and my average mu is going to be whatever I compute, $45,612, for example, right? We discussed that because of four reasons, right? First of all, very expensive. Second, very time-consuming. Third, can be very impractical. Fourth, not all the people will tell me the salary, so therefore, no matter how hard I try, I can't get it. Simple as that, okay? So I have to settle for the sample. And if I collect little n observations, my sample can be relatively large for me, but it's still small compared to the population. 2,000 people, right? Compared to the entire 160,000. it's less than 1%, but still a lot of observations. So my 2,000 people in the sample would be little n. Okay? And whatever I can compute from the sample, I'm going to call x bar. So mu is the population average, x bar is the sample average, and with all likelihood, they're not the same, right? What I can compute from the entire population is not the same as what results from the small, relatively small sample, okay? That's why I have two different notations, mu and x bar. Same formula, but different results, because one comes from population and another comes from sample. Okay, so that slide just puts that in the picture, what I just said, okay? If you add together things in the population divided by capital N, you get mu. But instead of that, you have sample, you add things together divided by little n, you get x bar, okay? So, all right. Arithmetic mean is a very popular tool for continuous data set, okay? So that's pretty much the weapon of choice when statisticians are discussing numerical or interval or continuous data, okay? And a lot of things can be measured. Not all of them, of course, right? Not all the variables that we collect are measurable in terms of numbers, but people's heights, weights, blood pressure, age, grades that they get in class, salary, temperature outside, humidity outside, stock market prices, right? Volumes of packages shipped by carriers. So all these things that are measured in terms of dollars, inches, cubic feet, degrees Fahrenheit, etc. Right? Mean is one of the most frequently reported measures. Okay. The downside of the mean is that it's relatively strongly affected by the outliers. Median doesn't have as bad of an effect by the outliers. So, for example, let's say regular neighborhood. Bill Gates decides to move in. Okay, for some reason. Whatever it is. He wants to live in the city of Newport News because it's close to the ocean. We have Busch Gardens around here, so why not, right? So let's say standard neighborhood with the median income with incomes around $100,000 to $200,000, right? So one household has $100,000 total income, another has $120,000, and we have $150,000. Bill Gates moves in. How much is Bill Gates' annual income? Probably measured in billions, right? I'm guessing. Capital gains on his holdings, right? Stock holdings. That's primarily the source of his money.
60 billion.
Yeah. So $1 billion, right? So what happens with the average? Before he moved in, the average was, well, let's call it around $130,000, right? Bill Gates moves in with his $2 billion annual income or something like that. That makes a huge jump in the mean, right? So therefore, arithmetic mean has this property that if you have outliers, and significant outliers, that means they're very far away from your regular group of observations, that can be strongly affected, that can strongly affect the average, okay? The outlier is something that does not look regular, doesn't look like the majority of your data points. It's either too high or too low, okay? Doesn't look like the bulk of data. Median, on the other hand, is the second, probably most popular measure for the numerical data set. And another thing is we can apply median to the ordinal data. In fact, we did it in the previous couple of classes, right? Remember, yesterday we ran the survey. What do you think about the parking at CNU? And you said 2, 3, 4, etc., etc. And then we kind of aligned them and picked the observation in the middle. That was median. So median applies to the ordinal data and also interval data, because interval data can be aligned from smallest to highest, right? So, for example, right here we have data set with 9 observations. 9 is a good number because it's odd. That means that you can find an exact observation, exact spot in the middle. So if we arrange them from smallest to highest, right here, okay, so it starts from 0 and it goes to 22. There are 9 of them, so position in the middle is going to be number 5, right? Because four numbers are under position number 5, and 4 numbers are over position number 5. So in the position number 5, we have 8. So 8 is your median, okay? Things get a little bit slightly more complicated when you have even number of observations. Then you don't have a number in the middle. It's either 5 or 4, right? So if I add 1 observation, so there are 10 of them, Number 8 is in the position number 4. Well, the problem is there are 4 below and 5 above, right? So it's not quite in the middle. If I choose the next one, number 9, then there are 5 below and 4 above. So it also is not quite in the middle. What statisticians do is a very simple thing. They take two numbers which are closest candidates and they average them out. So 8 plus 9 divided by 2 gives you 8.5. Even though it's not part of the data set, we can still say, hey, this is the median, okay? It separates 50% numbers below from 50% of the numbers above, okay? All right, and finally, mode. You've seen all these things in Math 125, correct? Yeah, so this is a refresher. That's why I'm not paying too much attention, basically. You're supposed to know all these things. Okay, mode is the most frequently occurring observation, okay? And if you have a nice distribution like this one right here on the chart, it's almost symmetrical, right? It's slightly skewed toward direction, by the way. To the right, because it has slightly longer tail extending to the right, okay? So it's a positively or right skewed distribution. But it looks not too skewed, almost symmetrical, right? So, and there is one peak, so it's a unimodal distribution, right? Slightly unsymmetrical, unimodal, slightly right skewed distribution. And because there is only one peak, we can say that this is the most frequently encountered class, right? In this distribution. So this is a model class. So in this case, mode makes sense as the measure of the central location, okay? Because it kind of looks like it's in the middle of my distribution. Well, here is the problem right there. Here's the problematic data set. If you look across all these numbers, you can see that except for zeros, everything else is encountered only once, right? Every number is just once in the data set, but 0 is twice, okay? Encountered twice in the data set. So therefore, 0 is your mode, and because we kind of position the mode as the measure of the central location, it's got to be the center of the data. Well, is 0 the center of the data? No, it's one of the extremes, right? So it's not measure of center. So therefore, mode can be misleading that way, okay? So therefore, as such, it's not very popular measure. And if I would have to rank mean, median, and the mode for the numerical data, I would pick mean first. Median probably is my second choice, and mode is the least preferable way to measure the center because of this argument right there. It can be misleading, okay? All right, now if my distribution is symmetric or close to symmetric, mode, median, and mean are going to be close to each other. In fact, if it's perfectly symmetrical, they're going to be exactly the same, right? Your peak is where your average is located, and at the same time, this is your median as well, because of symmetry, right? Half of the numbers below and half of the numbers above. Now, when your distribution starts to look like skewed distribution, like this one, this is also right skewed, by the way, right? Because it has the long tail going to the right. Then your mode, median, and mean starts to separate, and typically in this order, okay? So first you have the mode going on, that's the peak, okay? Then your median goes next, and then your mean, right? So mean is here because, essentially mean, I think of mean as the center of gravity, quite honestly. You add all these numbers and you divide by the number of observations. That's how physicists find the center of gravity, right? Add all the masses, multiply them by the coordinates, and divide by the total mass, right? So all of our points weight the same, so therefore mean essentially is your center of gravity, okay? So this long tail, if tail goes to plus infinity, even though the tail looks kind of small, but it propagates the very long direction, very far to the right. So therefore, it kind of balances out this relatively short end of the distribution on the left.
With submarine programming, we do what we call incline test.
Uh-huh.
You take the submarine at the pier and you pull it all the way to the right, all the way to the left, until it starts to almost topple over, but not. So that measures the center of gravity. Then we take the mean center of gravity, like you said. You don't want a submarine turned upside down.
Oh, absolutely.
Don't do that.
Yeah.
But,
Oh, cool. I didn't realize that.
you just actually want a submarine leaning way over like 45 degrees to the right or 45 degrees to the left. You pull it with ropes.
Mm-hmm. Oh, wow. All right. Okay, so mean, mode, median for interval data, if your distribution of the data is symmetric, they're very close, or they're all almost the same, approximately the same, right? So at the same time, usually the mean, that's basically to emphasize the point that I was trying to make before, right? Usually the mean is the first choice, especially when your data is nicely distributed. By nicely distributed, I mean it's normal or close to normal. Then the mean is your weapon of choice, okay? If data becomes non-normal, then mean kind of starts to lose its value. Here is a good illustration, okay? So let's say I have a bimodal distribution like that, okay? Like phone bills, for example. Phone bills were approximately distributed like that. If I would compute the mean, where would mean land itself? In the left part, in the right part, or in the middle? Well, if you have symmetric, kind of bimodal but symmetric. Yeah, mean is going to be in the middle, right here, right? So therefore you will say that, hey, my center is right here between the two peaks, right? Well, at the same time, somebody else can make an argument, hey, what about this part of the distribution? It looks like you have awful lot of data in the left peak, right? So therefore, if anything, center should be right here, but then somebody else can make another argument and say, hey, how about this part, okay? It's also pretty heavy, right? Because a lot of points there, so therefore another candidate for the center is right here. And if anything, actually mean, which is in the middle is where you have a valley, right? Valley means that you don't have a lot of observations in the middle, okay? So how come, if you have few observations, that is the most typical representation of your center of data? It's kind of counterintuitive, right? So therefore, when your distribution looks like that, bimodal, or severely skewed to the right, or to the left, like this, okay? Then mean is kind of losing a little bit its meaning. It kind of sounds funny, right? Mean is losing its meaning. But mean is not a good candidate. When you have this type of situation going on, mean is not a good representation of the center of gravity or center of data. So therefore, when you have severely abnormal data, like bimodal or trimodal or very highly skewed, the preferred way of measuring your center is actually median. Okay? And the mode is used very rarely for interval data, just like I was saying before. Okay? Now, ordinal and nominal data. Remember we discussed that in the previous couple of classes. They are highly underprivileged, right, compared to the continuous data. Why? Because they're essentially categories, and we just assign labels to them, numbers to them artificially, right? It's our choice. If you change the way you number your categories, all of your calculations basically go out of the window, pretty much, right? They don't make much sense anymore. They change. So therefore, when you're dealing with ordinal and nominal data, first of all, you can't compute the mean. That's number one, right? So mean is not an option. Okay. Ordinal data is well. Let's actually go to the other end of spectrum, right? Nominal data. The only thing that you can do with nominal data is compute the mode, right? And mode is not going to be the center because there is no center, right? It's just a bunch of boxes with observations falling into one of these boxes. Every observation can be placed in one of these boxes, right? So for the nominal data, you can't compute the mean, you can't compute the mode because categories are not ordered. Okay? The only thing that you can report is pretty much the most frequently encountered class, right? So you can report the mode not as a center but as the most popular response, right? Out of all of your categories, but that's about it. There is no mean and there is no median. The ordinal data is slightly more privileged, right? You still cannot compute the mean because it's still categories, which you assign numbers randomly. It's your choice, right? So there is no mean computation. Okay? But similarly to nominal data, you can report the mode, the most frequently encountered class or category, right? And also, you can report the median. Okay? So basically to recap, interval data, continuous data, all three measures are computable, right? Mean, mode, and median. Ordinal data, scale down. We drop out mean, right? Mean is not computable anymore. The only things, two things that you can do is mode and median. drop down one more level to nominal data. Now you lose not only mean, but your median as well. And the only thing that you have remaining is the mode, right? Make sense? Okay. But remember this thing, okay? That's probably one of the most frequently encountered mistakes that I see on the exam. Like when I have proportions, right? For example, let's say I have a problem. One of the homework problems that I'm going to assign actually is about gift cards. People either receive the gift card or they don't receive a gift card, and let's say we want to see, what percentage of people in society receive gift card on Christmas, right? Sometimes the error that I see is you have a data set which is just a bunch of zeros and ones, right? You either get it or you don't. Sometimes people compute the average, and the average says between the zeros and ones, the average is 0.075. What's the meaning of that? Well, 0.075% of people receive the gift card, so technically you compute the mean, but you can't really do that because 0 ones are my choice, right? I could as well call them 10 and 20, or minus 30 and plus 55, right? And that will change all of your computations. So when you're dealing with categorical data, that being nominal or ordinal, do not compute the mean, okay? Do not compute the mean. All right. Now let's talk about variability. Variability is another side of the same medal, pretty much. Data has the mean, and data has a distribution around the mean. Oh yeah, by the way, before we proceed, variability applies only to the continuous data, okay? There is no variability that is attached to the nominal data or ordinal data. They simply don't have any measures of variability, nothing at all. Okay, so from that point on, all we have is continuous data, okay? We're talking about continuous data. So why variability is important? Well, let me illustrate that with a graph, with a chart, okay? Let's say I have two different histograms. So two different data sets. One data set looks like this. And another data set looks like that. Okay? So you can see that this distribution, the first distribution, is relatively concentrated, right? It's kind of together, right? All the points, there is some variability around the mean, right? But all of the points, we can kind of think that that's where the majority of the points are going to be located, the majority of my data, okay? How about the second one? The mean is the same, right? Because the peak is in the same place. It's symmetrical, right? How about the data distribution? Is it more scattered around or is it more concentrated than the first one? It is more scattered around, right? So I can go much further to the left and to the right to cover the majority of the points, okay? So therefore, it's not enough just to say where the center is located. Where is your mean? We have to also say how variable are the points around that mean. And that basically is called measures of variability. So variability is inconsistency. High variability means high inconsistency, okay? Low variability means more consistency, right? Data are closer together, located closer together. All right, so let's start with a simple one, range. Range is very easy to compute, insanely easy to compute, okay? All we have to do is take highest and subtract the lowest. But as easy as it is, it's probably equally useless as the measure of the variability, and we'll see why. Well, right here, okay? First data set has only, 5 numbers, right? What do I have? I have 4, 4, 4, and then 50. So, by the way, by looking at this data, how would we call 50, number 50, compared to the 4? We have, the majority of data are 4s, right? We have 4, 4, 4, and then 50. So in this case, 50 probably is going to be an outlier, likely, right? Number that does not look like usual member of that data set. Now that's going to be our outlier. But regardless, that's still part of my data set, right? So highest number is 50, lowest is 4, range is 46, right? Now another set. Another set actually is more spread out, right? Still the boundaries are 4 and 50, but I have numbers in between fairly evenly distributed, right? So it's much more reasonable data set from that standpoint. Range is still 46, but these are two very different data sets, right? First one, I can say that 4 is my typical thing, right? That's the mode, definitely. That's probably the median as well, right? And mean is probably closer to 4 than it is to 50. But at the same time, ranges are the same, right? Two very different data sets. This is more uniformly distributed. This is more like a peak and one number on the outside, right? Range is the same. So what does that tell you? That range doesn't really care about numbers in between, right? It only cares about extremes, highest and the lowest. And it doesn't really look at anything else, okay? So we want a measure, some sort of the measure of the variability, which actually takes into consideration every single number in the data set. That would be more fair representation of all numbers, right? So therefore, ladies and gentlemen, here's the downside of the range, right? Shortcoming is it fails to provide information about the majority of data points. You can have 200 data points and it only cares about 2, right? On the far right and on the far left, that's it. So the majority of data points will not have a say, so to speak. So instead of that, statisticians compute something that's called a variance. Variance is, first of all, remember we discussed that there are computations for the population, they're called parameters, right? And there are computations for the sample, they're called statistics, okay? So something that we compute from the population is going to be different from exactly same something that we compute from the sample. So therefore statisticians use special letters for population measure and for sample measure. So for population, so you can see the trend, right? Statisticians use Greek letters when it comes to the population. And they use English alphabet letters when it comes to samples, right? Because before that we had mu for the population mean, x bar for the sample mean. Now we have sigma squared for the population variance and s squared for the sample variance. Now here is how the variance is computed. You don't have to memorize this formula, by the way. I don't expect you to. But there is actually a fairly obvious, simple intuition behind that. And what is it? What I want to do when I compute the variance is I want to see the spread. How far away are my points from the center of the data, right? So first thing that you do, obviously, is you compute the mean, right? You do that for the population, that would be mu, or you do it for the sample, that would be x bar. And that, by the way, immediately tells you what? For the ordinal and nominal data, there is no mean, right? I told you that about 5 minutes ago. Nominal and ordinal data, they do not have a mean. Therefore, they do not have a variance, right? So variance applies only to numerical continuous data, okay? No mean, no variance, simple as that. So first thing that I do is I compute the mean. And after that, x minus mu, that gives you the distance from the point to the mean, right? So let's say my x1 somewhere right here, okay? That would be one of my points. So if I take x1 minus mu, x1 is higher than the mean. That is going to be positive distance, right? From that point to the mean. The other point can be below the mean. That would be x2, okay? If I take the difference x2 minus the mean, that's my mean right there, okay, in the middle. If I take the distance, x2 is lower than the mu, that distance is negative. So if my mean mu is in the middle of my data set, some of the points will be below the mean, some of the points are above the mean, right? Some of the distances are positive, some of them are negative. What will happen if I add the distances together without doing anything with them? Positives will get bigger and negatives will pull it down, right? So therefore, if I just add the distances as is, right, as they are, positives will offset negatives, and on average I will get 0. Looks good, but doesn't really represent what's going on in my data. So therefore, I need to make negative numbers to look positive. And one way to do it is, of course, square them, right? So that's why when you compute the variance, here's the formula, right? The formula tells you to take the distances, x minus mean, and square them. The reason for that is we want to get rid of negative numbers. So even if the distance is negative, it still contributes to the computation of the variance, okay? And then you add the squares together and divide by n. Now note that there is a slight difference, right, between the formulas for the population, sigma squared, and for the sample, s squared. Statisticians, for the population, they divide by the population size n. For the sample, they divide by n minus 1. The reason for that is well, that's what any textbook will tell you. If you divide by n minus 1, you get an unbiased estimate of the standard deviation. Unbiased means that it's not over-predicting standard deviation, it's not under-predicting. It's pretty much staying right on target. Okay? But that's not important. We're not going to use that formula anyhow. I'm not going to ask you to compute variances or anything like that manually. All right. Now, let me tell you this, ladies and gentlemen. Where is my slide? Yeah. Variance is a weird measure. Okay? Why? Why is it a weird measure? Let's say let's say I have a data set, salaries. Okay? Salaries in the city of Newport News. So, all of my numbers, they have a unit of measure, right? What is it, unit of measure? Any number x in my data set is measured in terms of what? Dollars and cents, right? So my x is in dollars and cents. When I compute the mean, it's also dollars and cents, right? When I take the difference between x minus mu, I subtract dollars from dollars. The answer is in terms of dollars, right? But the next thing that I do is I square it, right? What happens when you square dollars? You get dollars squared. Have you ever seen dollars squared? No, me neither. And I don't even know what it is. Do you just take a dollar bill and cut the square out of that and that's your dollar squared? No. Same thing with temperature, right? If I measure the temperature in the city of Newport News, my x is degrees Fahrenheit, my mean is degrees Fahrenheit, difference is degrees Fahrenheit, and then I square it. It's even weirder, right? Degrees Fahrenheit squared. So therefore, we have a problem, Houston, right? So what do we do? How do we go from dollars squared back to dollars? Well, of course, you take the square root, right? And that's basically what happens here. Okay? Instead of variance, it's much more custom to use square root from variance, which is called standard deviation. And standard deviation is much more popular way to measure the variability. Okay? High standard deviation means high or low variability. High variability, right? Low standard deviation on the other end of the spectrum. What's the lowest, by the way, the standard deviation can be from this? Now let's go back to the variance. Obviously, that comes back to the question, what's the lowest variance, right? Because standard deviation is simply square root. What's the lowest variance that it can be?
Infinitely close to zero.
Infinitely close. Zero is the ideal case, right? If all of my numbers are exactly the same and I have no variability, that means that every one of my x's is precisely equal to the mean, right? And the difference between x and the mean is zero. When I square a bunch of zeros, I get zero. Average of zeros is zero. And therefore, you have a perfect case. No variability at all. Zero. So therefore, the lowest that the standard deviation can be is 0. And it's ideal case without any variability. Every single number is exactly the same. Make sense? Okay. Now let's talk about interpretation of the standard deviation. That's probably the most popular and the easiest thing to do, okay? There is an empirical rule, I believe it's called Kolmogorov's rule. There is a formula, Kolmogorov's formula, which basically says that if you go to the right and to the left from the mean, certain number of standard deviations, you will cover certain percentage of points. So, remember what I told you about the most popular distribution in statistics. It happens to be starts with n, ends with normal, right? Normal. Normal distribution. It's the celebrity in the statistical world, right? So it's a perfectly bell-shaped symmetrical distribution. It goes to the 0 on the right and on the left. And that actually, these are numbers that are coming straight from the normal distribution. If you go plus or minus 1 standard deviation from the mean, just like that, okay, on the first picture, you will cover approximately 68% of the entire area of the distribution. In other words, if you have something that's normally distributed, these are points really, right? And if you kind of align them horizontally along the horizontal axis, you calculate the mean, you go plus or minus 1 standard deviation. In these boundaries, you will have approximately 68% of all of your points, okay, that you have in your data set. Now, obviously, the further away you go, the more points you cover, right? So plus or minus 2 standard deviations will give you 95%, okay, of the area under the curve, or 95% of all your points. Plus or minus 3 standard deviations cover nearly darn everything, 99%. So beyond this point, plus or minus 3 standard deviations, you'll have only 1% of all of your data set, okay? So a lot of times, informally, people think about standard deviations having the width of plus or minus 3 standard deviations. That, of course, strictly speaking, is not true, because normal distribution is how wide? Oh, I mean, in terms of how far does it go? To the right or to the left? How far does it extend? Infinity, yeah, it's infinite, right? It doesn't end anywhere. It comes very, very close to the horizontal axis, but it never touches it. So it goes to plus or minus infinity. But 95% of that weight is contained within plus or minus 3 standard deviations. So informally speaking, a lot of people think about, width of the normal distribution to be plus or minus 3 standard deviations. Again, that's not true, right? Because strictly speaking, it's infinity. Okay, let's discuss yet another one, and after that we'll kind of switch gears and take a look at the problem. I believe the next one is the problem, right? Yeah. Okay, coefficient of variability. Coefficient of variation, sorry, not variability, variation. That's another popular measure, and it basically tells you what percentage is your standard deviation compared to your mean, okay? So it's also one of the standard things that are being reported when you talk about numerical characterization of your data set, okay? That is especially useful when you talk about things that are not directly comparable to each other. And you can see that CV, well, there are 2 flavors of CV, right? One CV is computed for the population, sigma divided by the mean, that's population. But if you don't know the population, which is true in the majority of cases, then we have our next best thing, right? What's the next best thing for the mean? X bar from the sample, right? And what's the next best thing for the sigma? It's your S, standard deviation from the sample. So S over X bar gives you the coefficient of variability. Multiplied by 100% basically tells you that oftentimes it's a relative measure, first of all, right? And it has no units, okay? First, like for example, let's say I measure salaries in the city of Newport News, okay? That means that my X bar is in salaries and my standard deviation is not salaries, dollars, right? Both measures are in dollars. I have dollars in the numerator and in the denominator. What happens if I divide dollars by dollars? I cancel out the units, right? So CV has no units of measure. That's why it's very useful when you compare things that are not directly comparable. For example, what's more variable in the city of Newport News, temperature or humidity? How do you measure temperature? Degrees Fahrenheit. How do you measure humidity? Percentage, right? Percent or whatever. Or barometric pressure, right? Pascal per square inch or something like that, right? Pounds per square inch. How do you compare degrees Fahrenheit and pounds per square inch? You can't, right? It's apples and oranges. So therefore, if you want to compare variability, you need to use coefficient of variation. You can't directly compare standard deviations because one is degrees Fahrenheit and another is pounds per square inch. Okay, completely different things. Okay, just to illustrate this last point, let's take a look at this problem. Okay. That actually has to do with operations management and logistics. Okay. Now, Patrick, you're going to be the management major, right? Which means that at some point in time you will take supply chain management course. Very exciting course, and I'm the one teaching it, at least right now. Okay. So big part of the supply chain management course is logistics and distribution. Okay. There is such thing as trucking industry. Okay. And in trucking industry, let me tell you a big secret about trucking industry. It's better to always ship a full truck load. Why? Because trucks, when you send a truck on the road, there is a fixed charge regardless of what's inside the truck. It can be completely empty, but you still have to pay trucker's salary, you have still to pay gas, you still have to pay the amortization of the equipment. So standard charges, they still apply. Okay, so it's cost per mile, exactly right. So therefore, it's best that you load the truck to the fullest extent because there is a fixed charge, but you move more items that way, right? The most that you can move. So on the per unit basis, is going to be the cheapest way to move. So full truckload is the name of the game in the trucking industry. Anything less than full truckload will raise your cost. Simple as that, okay? But trucks have two limitations. Number one is obviously volume, right? There is so much space in truck in terms of cubic feet. Plus, there is also such thing as weight. You cannot overweight the truck because, first of all, there are rules and regulations, right, on the road. Second of all, it will simply break down, okay, if you exceed the weight limit on the truck. So therefore, you can weight the truck out or cube the truck out, okay, in terms of the volume inside the truck. So what will happen first? Will you reach the weight, or will you completely run out of space inside the truck, right? That actually depends on what's more variable. Weight of the packages that you ship or volumes of the packages that you ship. So if volumes, for example, are more variable, likely what will happen is you will run out of volume first and still will not reach the truck weight limit. And other way around as well. If weights are more variable, likely you will weight the truck out and still there will be space. So ideally, you would like to limit, the truck both in weight and in volume, right? So that it's full truck and it's completely, at its capacity. Okay, so question is what's more variable, volumes of the packages or their weights? Well, one smart operations manager decided, what the hell, I'm not going to rely on the gut level intuition, I'm just going to get the data out, okay? So he takes 200 packages, and for every package he measures two things: how much it weighs and what's the volume, okay? Now this time around, actually what I did is I created, luckily, the, oh darn it, hold on. I'm going to again switch to the, alright, happens all the time for some reason, right? I'm going to duplicate the screens like that. Changes, okay. Alright, so this time around I actually uploaded the jump file out there on the Scholar. So let's go to the Scholar. Right here is the Scholar, courses, okay, and applied business statistics, jump data sets, and there is a file called weight versus volumes, okay. So let's download it, and it downloads as the jump file, so you don't have to do any kind of import. Well, from now on, that's what I'm going to do, probably. Okay? In some cases, I will still upload the good old Excel file, and you will have to import that, and maybe wrangle it with data types and set them up and stuff, right? But for the most part, we're going to deal with just straight jump files. Okay, so here's my jump file. Weight versus volume. So 200 right there, the number that represents, what does it represent? 200 is my, not population, sample, right? That's my sample size. Population would be millions and millions of packages, right? Here I have 200, that's my sample. Okay, so for this sample I have two things, right? Weights and volumes, okay? So question is, what's more variable, right? Do we have weights more variable, or do we have more variability in volumes? So let's do the distributions actually of both of these things. And this is, remember I promised to show you how to graph two things simultaneously. So here it comes, okay? I have two variables, right? Two columns, two variables. So let's click on the distribution button right there. And I'm going to pick, you know how to pick multiple things simultaneously using the mouse and the keyboard? You click on one, and how do you select the other one? Control, right? You hold down the control button and you click the other one. That selects both of them, right? And then I'm going to drag that pair into the columns and then click OK button. And that will create two distributions for me. And they are vertical because by default it shows things vertical, right? So how do I put them horizontal? Distribution stack. Kaboom. So here is my stack of distributions. Well, first of all, let's kind of chit-chat about them. What do you think, symmetric or not symmetric? Not symmetric, right? Slightly asymmetric, okay? So this one, and also modality. How many modes do you see? One on top, and probably one on the bottom, right? Well, you can make an argument that there is a slide right here, but that's probably a blip, right? Maybe a bunch of outliers, I don't know, but it looks like a unimodal. Both of the distributions are unimodal, right? Okay, any skew to the right or to the left? slight skew to the left, right? Because the left tail is somewhat longer than the right tail in both distributions, right? Okay. First of all, remember we discussed today so far what measures of central location, right? And we discussed measures like what were they? Mean, mode, and the median, right? And then we discussed range as the simple measure of variability, variance, and the standard deviation, and also coefficient of variability, right? Coefficient of variance. Okay, so right here is your summary statistics. These are probably the most popular things, right? And there are not a lot of them. We have a mean, but what's missing is mode and the median, right? We have standard deviation, but we're missing range, CV, and also variance, right? So let's add them, okay? How can we add them? Very easy. You go to this red triangle right there where it says summary statistics, and you say customize my summary statistics, okay? So you click on the customize, and whatever is missing, we can just go ahead and pick. So let's see, what do I want? Variance. Even though variance, I told you, variance is not very popular, right? Because of its weirdness. It's units squared. So in my case, it's going to be like pounds squared. What is pound squared? I don't know, right? So, but anyhow, I'm going to add variance to the list of things. CV, okay, then range right there. Also median and the mode, okay? And it basically does that for weights distribution. Let's do the same thing for the volumes distribution. So customize summary statistics, and I'm going to do the same thing, right? I'm going to add variance, coefficient of variability, then mean is there, median, mode, and range, right? That's what we did for the first distribution. And I click OK. So it's very easy, straightforward to get your basic statistics, right? Even if you see something missing, there is a comprehensive list. You can get anything you want. Well, first of all, let's take a look at the mean, mode, and the median. So for the weights, the mean weight, and I'm guessing that's ounces, right, or something like that. 26 is the mean, 25.9, which essentially is 26, is the median, and my mode is 23.6. So they're very fairly close to each other. What does that tell me about the form of the distribution? Mean, mode, and median are close. What does that normally tell me about the form? Is it symmetric or is it completely out of shape and skewed? Pretty symmetric, right? It's PDS, pretty darn symmetric. That's what I call it. PDN, pretty darn normal. PDS, pretty darn symmetric, okay? So that one is pretty darn symmetric. Well, with the second one, probably in a slightly worse shape. 8.8 is my mean. 8.8 actually is my median, so that's exactly the same. And my mode is slightly off, 7.5, but not terribly off, right? So this one is also pretty symmetric distribution. They're nice. Okay, but the original intent was, remember, we wanted to discuss the measures of variability, right? So what's the most popular measure of variability? It's the standard deviation, right? And the rule is high standard deviation means high variability. Low standard deviation, low variability. So on the face level, on the face value, so to speak, of this problem, all I have to do is compare two standard deviations and I'm done, right? So let's take a look. Weights. Standard deviation is, where is my standard deviation? Right there, 4.03 for the weights. Volumes. Standard deviation is 2.7. That's it. End of story, right? Because 4.03 is certainly greater than 2.27. So therefore, if I would not be familiar with statistics, I would say clear as day that my weights are more variable than my volumes, right? Because 4.03 is more than 2.27. But I took a class, BUS 31 at CNU, right? And there, they taught me that you can't compare apples and oranges. And that's exactly what I'm doing here, right? Because I'm saying that 4.03 pounds, right, is higher than 2.27, whatever it is, cubic inches, maybe, right? I'm comparing weights. It's like to say that, $10 is more than 12 degrees Fahrenheit. That's just stupid, right? It's apples and oranges, literally. So in this case, because I have a unit conflict, right, I can't really compare them by the face value, right? I can't use the standard deviation because it has units. So I have to use a unitless measure, which is what? Which measure of variability has no units? Coefficient of variation, right? CV. Remember it because it has sigma over the mean, or S over the x bar, in which case units cancel out and you have just a number, right? So, therefore, I have to actually compare CVs. So what do I see? On the weights, my CV is 15.49, and on the volumes, my CV is 25.75. So what does that tell me? That actually volumes looks like they are more variable than the weights, right? Contrary to what contrary to what we thought originally, based on just the standard deviation comparison. So therefore, the tracks are more likely to do what first? Weight out or cube out? Volumes are more variable than the weights, right? So therefore, tracks are likely more to cube out first, right? As opposed to weight out, okay? According to my analysis. Make sense? And that actually is a pretty big deal because, two extremes, right? What happens if I load the track with bricks? What will happen first? Cube out or weight out? Weight out, right? Because cubes are relatively small, right? Bricks are relatively small, but they're heavy, right? What happens with it if I load the track with pillows? What will happen first? Cube out or weight out? Cube out, right? Because pillows are very light and they're pretty bulky, right? But really, whenever we really ship the exclusively bricks or exclusively pillows, right? If we do that, then there would be virtually no variability, right, in terms of volumes and weights, right? They are identical, pretty much. So different people ship different packages, right? You ship a whole bunch of stuff to your grandma in Fresno, California. It's pretty light package, but it's really bulky. Somebody else ships, heavy, some piece of electronic, right? Computer, for example. And it becomes relatively heavy. So therefore, there is a variability from package to package. And that basically tells that the volumes are more variable than the weights. So tracks are likely first cube out before they weight out. So there will be still limit on the weight, but there will be no room remaining in the track. Okay? Make sense? Okay. Jolly good. Do you want to take a 10-minute break and then do the last final piece? All right, let's do that. Okay, so so far we discussed two numerical measures, right, that relate to mostly continuous data, numerical or interval or continuous data. Measures of central location, we discussed mean, mode, and median, and measures of variability. The simplest one was range, and we said, well, if you take variance, it actually considers all data points in your data set. But it's weird because it squares the unit. If you take square root from that, you get down to the standard deviation, and that's normal to use standard deviation, right? But when you're comparing things that are not easily comparable against each other, such as, weights versus volumes or temperature versus atmospheric pressure, units are different, so therefore you can't really compare standard deviations. Then you have to choose the coefficient of variability. The last piece of the puzzle that we have to consider today is measures of relative standing. What is that? I'm sure you heard about that in your previous classes, such as Math 125, and you heard that before as well, actually. Percentiles, that's what we mean primarily, as the measures of relative standing. So what are the percentiles? Percentiles, actually, they refer to the individual observation. So measures of central location and variability, these kind of talk about the entire data set, right? Most of them anyway. Range doesn't really look at the entire data set, but the rest of them, CV, standard deviation, variance, that takes into consideration the entire data set. So these things that we discussed so far, they kind of relate to the entire data set. Percentiles, on the other hand, speak about one single observation as it stands compared to the rest of the data. Okay? So what's a percentile? Percentile is the basic kind of unit of measure as far as the relative standing is concerned. Percentile number pth percentile, is a value in your data set that separates p% of data below that number from 100 minus p% of data that's above that number. That's basically a standard definition. And a lot of times percentiles are actually being used. For example, how many of you in the future are planning to go to the master's or MBA program? Okay, Christian? All right. When you go to the... You too? Yeah. That was actually my plan at some point in time, but then I went for PhD. So I guess it's too late for me to go back to the MBA. So when you apply to the MBA program, I mean, every student likes it, right? You go to the website of the university and they say clearly how many points you need to get on your GMAT test to get in, right? Same applies to SAT. I have an 18-year-old daughter. We just went through this fun period of applications and waiting and being nervous and psychotic and all that, right? So it would be nice if universities would post numbers, right? So for example, if you score, I don't know, 1,300 in SAT, and we accept you. Problem is, they don't, right? Not a single university says that, hey, this is what you need to achieve, right? They keep it vague, and that's done on purpose because they don't want to exclude anybody, right? Because it all depends on how many people will apply and what kind of scores will they see, right? If they see very high scores, right, and they have no reason to go low, right? So therefore, this year, when we have a especially strong pool of applicants, we'll take high scores. So if you scored, for example, 1250, sorry, this year it was not enough because we had a especially strong pool of applicants, right? So typically, universities don't look at the scores, but rather they look at the percentile. So what does that mean? For example, GMAT test. When you're taking GMAT test, it's not just you, it's thousands and thousands of people all over the world in all kind of countries, right? And sometimes you have a strong group, sometimes you have a weak group, right? So you may score relatively high in terms of numbers, but if everybody else scored high, you're not that different from the rest of the group, really, right? So it does not tell the university anyhow, are you a better candidate or worse, because everybody else is pretty much the same. So therefore, universities typically, they don't look at the scores by themselves, but they look rather at the percentile. So percentile tells you how high or low you scored compared to the group. So for example, let's say you scored on the GMAT, I believe 700 is a very good score, 600 is also a decent score, right? Let's say you scored 620 on GMAT, which is a very decent score. Universities would rather look at the percentile. So basically it will tell them, compared to the rest of the people who took this exam, how many people you were able to outscore. Okay, so in other words, what percentage of people scored lower than you. So if your score corresponds to 60th percentile, that means that 60% of all test takers scored lower than you. So you outscored them, and you scored below 40% of the top people in the group, right? That's simple as that, okay?
Well, what Mary does, they take your GPA times your GMAT score, and then they calculate that from that,
Mm-hmm.
calculate a percentile. So if you met a certain percentile, then you're in, and you're not, then you're out.
Yeah, you can do all kinds of manipulations, right? Yeah, not a single university looks exclusively at SAT. In fact, I read, I believe that SAT is not a good predictor of the academic performance by itself. Why? Because, well, first of all, it's just one exam, right? You get lucky just purely because, you got questions that you knew, you scored high even though your grades weren't so high. That can happen, right? On the other hand, you can be very smart and just didn't have enough sleep, right? And panicked at the exam, that happens also, and you scored low. Plus, you can take them multiple times, right? Let's not forget that. So as opposed to your GPA from high school, which shows your distributed effort over a number of years, right? As opposed to getting lucky or unlucky on one exam, right? So therefore, universities, they look actually at a number of different things, not just at the SAT score. Okay, so obviously, percentiles can range from 0 to 100, right? 0th percentile means what? Well, let's actually, here, I like to draw this type of illustration, okay, when I talk about percentiles. Well, let's say that all of my data set is a horizontal line, okay, ranging from some minimum at the low end to some maximum on the high end, okay? So if I have the minimum right there, that's my number on the far left. Which percentile is that? That's percentile P sub 0, I would make an argument. Why? Because how many, what percentage of data set is below my minimum? Nothing, 0, right? And 100% of my data set is above that value, correct? Simple as that. So by the same argument, if I go to the far right, my maximum, that would be my percentile number 100, right? Because 100% of the data is below my maximum. Excuse me. And nothing is above, right? And everything else is in between. Obviously. So my percentile should be between 0th percentile and the 100th percentile, right? So quartiles. Quartiles are standard measures of relative standing. And they're standardly reported, actually. Every time when we run an analysis of the numerical data set, you will probably see quartiles as the standard thing to report. Okay? So, 3 quartiles. We have Q1, that's first quartile, which is the same thing as the 25th percentile, P25. Okay? Then we have second quartile, Q2, which is the same thing as the 50th percentile. Now, 50th means what? 50% of the data below and the 50% of the data above. And we actually talked about this measure today, and we called it median, right? Median separates 50% of the data below from 50% above. So your second quartile or 50th percentile is the same thing as the median, okay? And then there is a third one, Q3. That would be 75th percentile, P75. Okay? All right. So this distance between your first quartile and the third quartile is called an interquartile range. And actually, it's another measure of the variability, which I didn't mention before because I was waiting for this exact moment when we discussed what quartiles are. So what does that tell you? Interquartile range. True or false? Below my Q1, I have 25% of the data. True, right? Because it's 25th percentile, right? So 25% of the data is below my Q1. True or false? 25% of the data is above my Q3. True, because it's a 75th percentile, right? So what percentage of the data do I have in between Q1 and Q3? 50%. And that's 50% of the data in the middle, right, of the data set. Because 25% below interquartile range and 25% above interquartile range. So this is another way to characterize the data variability. Sometimes it's also reported as the measure of variability in the data. Okay? It represents the variability of 50% of data in the middle. Okay? Make sense? All right. Oops. Hold on. My computer reports to me that I need to plug the power source or else it's going to cut off. And we definitely don't want that. Amazing actually that it took almost 2 hours. Typically it runs out of juice quicker. Okay, we're good to go. All right. That is something that I found yesterday actually on the CNU website. Okay, admissions for freshmen, SAT or ACT. So it's basically information about admission standards and criteria for CNU for incoming freshmen, potential freshman students, right? Yep, note these 2 numbers right there, okay? So CNU actually reports, remember I told, we had this discussion just a minute ago, right? That universities have a moving target, right? So they want to score, as high as possible. So every year when CNU admits new students, Paul Tribble, the president, he has the speech basically that he gives at the beginning of the year, and he says that we admitted so many students. The average SAT score was this. I believe every once in a while he mentions also this thing. But you can see that it says the middle 50% of reading and SAT math was, in the fall of 2014, was between 1070 and 1230. So
43 years ago when this school existed, and I was applying, the median score was between 4 and 600.
4 and 600.
To get to this school.
Things changed quite a bit. Yes. Yeah.
This was the fallback university.
Oh, absolutely, yeah. CNU definitely made huge strides, especially in the last 20 or so years. Yeah.
I think it's the 6th hardest school to get into.
Yeah, I believe it's like 3rd most selective school. I read it recently. Like 1st most selective school is UVA, I believe, or William and Mary.
You guys are practically walking on water.
Yeah, that's true. So CNU, as you can see, what does that mean? The middle 50% of the scores are between 1070 and 1230. So what are these two numbers? That's your Q1 and Q3, right? That's what CNU reports, okay, on their admission page. Interquartile range, that's what it is, okay? So it is very practical. It's not just a bunch of, statistician trickery. All right, now box plots. Actually, we've seen box plots before. I didn't want to emphasize that, but we'll say it again, okay, in just 1 second. What's a box plot? Box plot is this thing, really, that I have on the board. And typically, there are like 5 elements on the box plot. Well, number 1 is it has the minimum observation and the maximum observation. So these are your extremes, right? Then there is a box in the middle, and the box is made around the interquartile range. Okay, so lower boundary of the box is your Q1, upper boundary of the box is your Q3, okay, 25th and 75th percentile, and there is also a line inside the box, can be in the middle, can be towards the high or low end. That's your median, or second quartile, or 50th percentile. So the box is really a rectangle which is built around your Q1 and Q3. So this is your interquartile range. And then the way box and whiskers plot is constructed is we have to draw a whisker. The highest, the maximum length of the whisker can be 1.5 times the interquartile range. Okay. So, for example, let's take a look at this picture on the slide. Okay. What happens on the left side? On the left side is we started to draw the whisker, and the whisker begins at the box, right? Which is around the interquartile range. So, if we reach out the lowest observation with the whisker, which happened in this case, and we still did not reach the maximum length, 1.5 times the interquartile range, then we just terminate the whisker and say, hey, we touched the minimum, as in the case on this slide, right? And that's it. That's where the whisker ends. So there are no outliers. On the right side, you can see things are a little bit different, right? We actually kept going with whisker, and we reached the highest, the maximum length, 1.5 times the interquartile range. That's where we have to stop. And there were some points that we didn't reach still. And these points are called outliers. So that's how statisticians formally define an outlier. If you cannot reach a point starting from the box with the maximum whisker length of the 1.5 times the interquartile range, we declare that these points are too far away from the majority of the data, from the center, okay, from the 50% of the data in the middle. And therefore, we call these points outliers. That's essentially how outliers are defined in statistics. Remember our discussion before about the phone bills, right? $0. Is that too small? I don't know. $120. Is that too large compared to the average? I don't know. Well, that's basically the way how to strictly and rigorously define the outlier. If you cannot reach it from the box with 1.5 times the interquartile range whisker, that's too far. That becomes an outlier. Okay. All right. So let's take a look at, and this is going to be our last problem of the day, right? Let me just see. Yeah. And I have to show you the custom percentiles. Okay. Time in the restaurant. So let's take a look at the problem. For many restaurants, the amount of time, how long customers sit and drink their coffee and eating a dessert can be an issue that affects the profit. So in other words, they want you sit down, eat quickly, pay, and leave, right? That's the idea. And, get the table free for the next paying customer. Okay. To learn, it says to earn. To learn more about this variable, how long people spend in the restaurant, a manager of the restaurant decided to track 200 groups of people that come in and eat, okay, at the facility. So from the moment when they sat down at the table until the moment when they stood up and left, they basically tracked the time, okay? And let's take a look at the data. So the data are, and again, I need to see what happens. I have to reset every time when I restart the recording video, right? I have to reset. Why? Changes and okay. All right. So let's go to the Scholar, and here is the jump file. So I converted that to jump. All the data are there, 200 observations. So download the restaurant.jump.
So in Visa, you have to save it into a directory and then open it from Visa. This is, you can open it directly, just pop right into jump automatically.
Yeah, but it still downloads onto the computer.
Yeah.
So this
You
thing,
have to save it somewhere.
yeah, it saves in download folder. Yeah. Uh-huh. So let's open up the file. And here's the file. So 200 observations, right? You can see that. Number of rows is 200. All right, so let's take a look at what do we need to find out about this data set. First of all, construct a histogram and tell what you see. Is it symmetric? Is it asymmetric? Is it skewed to the right, to the left? Is it bimodal or unimodal or trimodal? What is it? And then calculate mean, mode, median, range, standard deviation, 25th and 46th percentile. Are there any outliers? So let's get going. All right, so here is my data. Right, first things first, let me take a picture. And that's actually good practice in statistics. Before you start jumping into the hypothesis testing and confidence interval, etc., it's pretty much a good idea. Plot a picture and tell what you see. Okay? Before you do the analysis, just evaluate things visually. What do they look like? Okay. So you remember how we plot the histograms, right? Or any graphs for that matter. So we have to click on the distribution, and here is the only column time. I put it into the Y columns. Click OK, and here is my distribution. Well, the only thing is let's put it horizontally, right? So let's stack it, and there it is. Okay. So here is my histogram. What does it look like? Well, first of all, it's obviously not symmetric, right? Also, what about the modality? It kind of look a little choppy, right? A little weird. But I don't think that these spikes that I have, this spike, and this spike, they are regular spikes that indicate something. You know, most people would like to stay either 25 minutes or 30 minutes or 35 minutes. These are probably noise, right, that I'm picking. So the shape of the distribution probably is smooth, right, because there's nothing special, not from the general standpoint about 25 minutes versus 30 versus 35 minutes. There should be no spikes. Okay, so I would say that this is probably a unimodal distribution, and it's skewed to what direction? To the right. Okay, so we have a lot of people that basically come in, sit for 25 to maybe 30 minutes, right, and 20 to 30 minutes, and then they leave, right? And then there is a long tail, but there is relative. The longer the wait is, right, the longer you spend, the fewer people you see that spend that kind of time at the restaurant. So it has a right or positive skew. Okay. The average time you can see 2.93, so let's call it 30 minutes, right? On average, people spend half an hour, which probably is a reasonable time, right? You go to the restaurant, you sit down for 30 minutes, and then you leave. Okay. Now, the only thing that's not showing up, the only things that are not showing up are mode and the median, right? So let's show them. So how do we do that? We have to customize our display, right? So custom settings, and let's also do the range. And where is my median and the mode? They're right there. Okay. All right. So mean is, well, let's start actually with the mode, because remember we discussed that if the distribution is skewed, the first thing that comes typically, especially if it's right skewed, right? You have a mode, first thing, right? And the next one is median, and probably the last one is mean. Now let's see if that's the case. Mode is 25, that comes first. Median is 28.5, that comes next. And the mean is 29.9, oh, 30, right? So what we had on the slide before is actually true in this histogram, right? Right skewed, first you have the mode, then median, and then the mean, okay? So the fact that the three are separated, that also tells you that there is a skew, right, in the histogram. Okay. Now what else did we want to look at? Range and standard deviation. Well, standard deviation is, well, range first of all, right? Range is 34, so the difference between the longest people, right, the people who spend the longest, the people who spend the least, so it's approximately between 20, according to my histogram, right? 20 is probably my minimum. Where is my minimum? 21 actually, right? And the highest is 55 right there, okay? So the distance indeed is 34, okay? And the standard deviation is 5.99, so I call it 6. So this is not a symmetric distribution, but still the general rule applies, right? If I go plus or minus 1 standard deviation, you get approximately 68%. Plus or minus 2, 95. Plus or minus 3, you get approximately 99, okay? So 6 minutes is my standard deviation. Now percentiles, right? So the first question that I have is, where is the 25th percentile and also 46th percentile? Well, 25th percentile is the standard thing, right? We call it first quartile. And you can see that, I told you before that typically Q1, Q2, and Q3 are reported, right? Whatever analysis you run, any software will probably report first three quartiles, right? And it's right there. You can see that. 25th percentile, quartile 1, that's your 26, right? So my P25 is actually 26 minutes, first quartile. My median, 50th percentile, is 28.5, and it's also reported right here as well, right? Median is reported twice because it's median and the second quartile as well, okay? And my 75th percentile, quartile number 3 is 32 minutes. So I can say that 50% of data in the middle, 50% of the typical customers, right, at the restaurant, they spend anywhere between, what, 26 to 32 minutes, right? That's pretty tight range, right? 50% of customers that are typical at the restaurant, they sit, the width of the range is actually, what, 6 minutes, right? Pretty tight. Okay. Now, 46th percentile is custom, right? Because it's not standard. So what do I do for that? Well, I have to go to, I believe, display options. Okay, so here, the red triangle, the second red triangle. Okay, I want to go to display options, and the third item on the menu will say custom quartiles. You see that? Display options, custom quartiles. Did you find it? You don't have it on Mac?
Which one? What was the first step you did? You clicked
On the red triangle, right there.
and then
Yeah.
it goes to,
Display options,
okay, and
custom quartiles, or what is
then, there we
it?
go, yeah.
Quantiles, right? Custom quantiles. Okay, so here you can see that I can actually type what I want, right? So 46th percentile course, and it's a fraction between 0 and 1, right? So 46th percentile corresponds to 0.46, right? And that's what it is. And when I click OK, it just basically adds another part, okay, another report to my output, where it says that here, quantile number 46 correspond to 28 minutes. Okay? Make sense? So it's very easy, right, to find custom percentiles. Okay? Yeah, let's actually talk about outliers first, and then we come back to this question. Find such time in the restaurant that 60% of customers spent longer than that. Okay? Outliers. Remember, we just discussed outliers, and what did we say? Outliers can be found on the box and whiskers plot. And what we had on every histogram that we looked at so far is box and whiskers plot. So it's there for you by default. Okay? I just didn't want to emphasize that at this point when we first looked at the histogram, but now it's time. Okay? So on the top of any histogram, let me make it bigger actually. Like that. Okay, on the top of every histogram, we have a box and whiskers plot. So you can see that this is my Q1 right there, right? This is my Q2 median. That is my Q3. The box is built around. So this is my interquartile range essentially. Okay, and whisker number that goes on the left is short, right? Relatively short. So that means that I reach the minimum, and that's where it stops, right? Okay, whisker that goes on the left apparently is terminated at the maximum length, which is 1.5 times the interquartile range. And whatever I was not able to reach with the whisker is an outlier. So these are my outliers, right? What happens if I point to them? It basically tells me, right? Every outlier I can find numerically what it is, 43 minutes. If I want to look at them all I have to do is select them using this box, right? Selection box. Come on. Okay, like that. Okay, so I selected them. And you can see that immediately it shows me where they are located in my histogram on the distribution, right? Obviously, in all these bars on the right, okay? But what I can do is go back to my data, and all of my outliers will be highlighted. These are probably at the very end. I'm going to move slowly, actually. Come on. Yeah, they're all at the very end. Move slow for some reason. Okay, let me. Yeah, it will not allow me until it scrolls all the way back down. It will not allow me to go back to the analysis. I'm almost there. Yep. So these are my. Oops. Let's go back. These are all of my outliers right there. Okay, at the very end. So anything longer than apparently 42 minutes or more, right, is an outlier. So if you're in a restaurant and it has been 3/4 of an hour, you're sitting too long. That's unusual, okay? It's time to get up and leave. That's basically what it says, right? Okay, and the last question of the day, let's address that one as well. Find such time that only 60% of customers stay longer than that time. So for that, I'm going to draw on the board a kind of schematic representation of our data set again, right? So all of my data is somewhere between my mean and max, okay? That's my 0th percentile, that's my 100th percentile. What I'm looking for is somewhere over here, right? P question mark, whatever it is, right? What percentile is that? I don't know yet. But what's given to me is 60% of customers stay longer than that. Which means that on the right, from that number, I will have 60% of my data set, right? So, what percentage should be on the left? Less than that value. 40%, right? So therefore, by definition of the percentile, that would be percentile number 40, right? Percentile number 40, right? It separates 40% of data below that from 60% of data above that, okay? So this question was formulated in a little bit of the tricky fashion, right? I don't tell you to find 40th percentile, but rather I formulated differently. I said, longer than that time, we have 60% of customers. That translates into 40th percentile. So all I have to do really is go back to analysis, to jump, right? And again, do the custom percentile. So I did one of them, it was 46. So the next one that I have to find is 40th. So again, I have to go to the red triangle, display options, custom quantiles, and here I have to type 0.4, right, for the 40th percentile, and you click OK, and it says 40th percentile is actually 27 minutes. Okay. All right, so I believe this is it pretty much. All the slides, they repeat the same steps as we did. Okay. Yeah. So if you want to remove the outliers, right? Let's do that actually. Kind of useful, can be useful exercise. So if for my analysis I want to exclude the outliers because they are outliers, they are not typical, right? So I want to see what typical looks like. So what do? I just basically right click and say exclude all these observations, right? I don't even have to hide them. Basically the stop sign tells jump that whatever I do, data is still there, but it's not part of the computations, okay? So, and you can see how many of them, by the way, I have? 11, right? Excluded 11. So let's actually redo the analysis, right? And let me show you one more cool thing, actually. This thing is simple, but later on, like in a more complicated type of analysis, I may need to rerun this thing, right? Jump actually remembers what you did in the previous time, and you can recall it. Okay, so if I click on recall button right there, it just basically places, like last time what I did is I placed time right there, and it does the last settings that you did, okay? So this is very simple, it's just drag and drop, but in a more complex settings, such as in my class data analytics, you have to, like for example, you have 30 columns, and you want to build a model with one column as your Y, and bunch of X's, but not all of them, you select them, right? So out of 30 columns, you select, say, 15. So I don't want to click and select them, I can just click the recall button and it brings over everything that I did last time. So, and then you click OK, and there is your distribution, and number of observations you can see now it's 189, 11 excluded, right? It was 200 originally, but I excluded 11. So now it's a different distribution which excludes the outliers. And you can see now that my box and whiskers is clean, right? Doesn't have any outliers listing, right? Because I removed them, okay? Now, of course, that changes things, right? Because I removed 11 things, 11 observations from my data set. Now all my quartiles are different, Q1, Q2, Q3, right? My interquartile range, everything is different, but still took care of the outliers. So now with outliers removed, seems like a clean distribution, okay? Without any unusually high or unusually low observations. Make sense? Okay, so ladies and gentlemen, I have homework number 2 posted, I believe, right? And it's one problem. So it's a problem that carries over from yesterday because we didn't have time to finish the histograms. And the second part of this problem actually asks you to find custom, percentiles and interquartile ranges and other things. Okay?
Just to clarify, you said it's question 3 on the
Yeah. So it's posted out there as homework number 2.
Yeah.
Okay.
So you just download homework number 2 and do it. Okay? So you can. Yeah. So you can email it to me just like you did before. Okay? That's it for today.